Hello friends and welcome to Average Classes. Do you know that the engines and cabins of cabin crew in a submarine are kept low? Why we keep it low? No, lower portion. Then iceberg, the vast portion of the iceberg is actually submerged, that is 90% is actually submerged, only 10% is visible. Do you know in Dead Sea is so dense that you can actually float with more of your body outside? Okay, do you know the hot air balloon cabin position is also at the lower, and how it works? Okay, do you know at what altitude the helium stops moving upward, helium balloon or the balloon keeps on moving up? Why is it so? Do you have any idea why a ship of steel, it floats on water, but at the same material, steel, a tiny steel pin, it sinks? Okay, do you know what happens if a ship moves from a sea water to river water? Well, the answer to all these questions is your buoyancy. It's a very lovely topic of your fluid mechanics, and we are gonna find out all the answers throughout our class. So watch the video till the end and learn in one go itself. Okay, and you haven't subscribed to the channel yet, please do subscribe. Now let us dive into our lecture, okay, with the help of a simple experiment. Okay, so as you can see, I have some liquid here. You can see the liquid level. Okay, you can see the liquid level. If you want, you can mark the liquid level also. Okay, so you can mark the liquid level also. Okay, now what I have done is I have took an apple. Now what I am doing, I am inserting this here. So now clearly you can see the water level is above the marked line. The water level is above the marked line. Okay, and now as you can see, I am pushing this apple down. I am trying to keep it down, but what happens? It comes up. What happens? It comes up. That means there is something present in the liquid which is pushing the body up, and acting against the gravity. As here also you can clearly see the liquid level has now increased to this. That means, okay, this particular apple, when it is going inside, it is dispersing the liquid. It is occupying some space. So it is dispersing the liquid, but liquid cannot go anywhere. It is confined, so it cannot go left side, it cannot go right side, it cannot go down. It has been confined from all the surroundings. So which is the only side it can move? Upward. Only side it can move is upward. So it has created some space, okay, and as the liquid cannot go somewhere else except than the upward side, the liquid level has moved up. How much it will increase? Same, how much volume your apple has occupied. Same amount of liquid only it will displace. So this upward thrust, what the liquid is giving to this apple is known as your buoyancy. Okay, buoyancy is a tendency, and the force of buoyancy is a force. Its unit is Newton. Okay, so how to quantify this tendency of buoyancy? Quantify means we need numbers. Means we need to have a magnitude. Okay, now let's find out this magnitude with the help of this. So I have took a haphazard cross-sectional shape, okay, who's having an area A. So this area or this area, how much? This area is your A, and the height of or the depth of this particular object is H. Depth of this particular object is H. Let us say this object is at a depth S from the free surface. We know what we know. Okay, sir, there is some pressure acting on the top surface. There is some pressure acting on the bottom surface. So the pressure force acting here, already we have discussed this hydrostatic forces. Okay, hydrostatic forces. So what will be the hydrostatic force on the top? Sir, it will be rho G S A, the distance from the top. And we know the forces on the bottom side will be more. And how much will be your F bottom? Sir, it is rho G S plus H into A. S plus H into A. So what is the net force acting on this? What is the net force acting on this? F net. Sir, F net equal to your F bottom minus F top. Acha, F bottom bhai, sir, rho G H S plus rho G A S plus H. Very good. Minus, sir, this is rho G S A. So if you will solve it, what you will get? Sir, I will get rho G H A as the F net. The net force. What is H? Where H is the thickness of this particular plate or the solid. This solid is completely submerged inside the liquid. Solid is completely submerged inside the liquid. We are considering a case where it is completely submerged. Okay. First we will study about submerged cases. Then we will go to your flotation. Okay. So rho G H A. Now what is A? Sir, cross sectional area. What is height? H height. What is your volume? Sir, area of the base into height. Area of the base into height. Acha, sir, you write here density F, sir. We are getting confused. So this is density of fluid. Density of fluid. Okay. So density of fluid rho F. G H into A is what? Volume. What is this? Sir, volume of solid. This is your F net. And F net is your force of buoyancy. Force of buoyancy FB is rho F G volume of the solid. Do not forget, please. This is what? Density of fluid. This is your volume of solid. Volume of solid. So your buoyancy force, it became FB equal to rho F G and V of solid. That is volume of the solid. Very good. Very, very good. Now see. So this force of buoyancy, this is the magnitude. What is the unit? Sir, unit is Newton. Unit is Newton as it is force. The magnitude of the buoyancy force is density of the fluid multiplied by acceleration due to gravity. Acceleration due to gravity multiplied the volume of the solid submerged. Multiplied volume of the solid submerged. So what we come to know? We came to know that the force of buoyancy does not depend on the density of the solid. In case it's the density of the fluid. Now G is the acceleration due to gravity, V is the volume of the solid. That means irrespective of the shape, any shape you take, shape does not matter in case of buoyancy force. Volume matters. Okay, what doesn't matter? Depth of submergence. Depth of submergence doesn't matter. Whether anywhere S term is coming here, no. So you keep it 1 meter below, 2 meter below, 10 meter below, 15 meter below, 100 meter below, 200 meter below, the buoyancy force is going to be the same. So your depth of submergence does not come into play when you are talking about buoyancy force. Okay, see, I'm going little slow. Try to understand. Buoyancy force is very interesting. So FV means more the buoyancy force, in order to have a higher buoyancy force, my density of the fluid should be more. If the density of the fluid is more, buoyancy force is more. That's why, like we said, in Dead Sea, okay, where the density is 24% more, so buoyancy force is more, you can actually float more of your body above the water. Okay, or how you can have more higher buoyancy force? Sir, the volume of the solid should be more. We will come to that 1 minute and I'll come here. Okay, I want to prove why your any solid, any shape of the size, it doesn't matter for your buoyancy force. Okay, let us take same. I am taking now a shape which you will all understand. So now we have took a container. Okay? Now in this container I have a cylindrical shape. Okay? Now this is familiar. Now this example is going to be little more familiar. So I have a shape of a cylinder. Okay? Now the height here is h. The height of the cylinder is h. Let us say the cylinder is at a height of h1 from the surface and the bottom portion is at the height of h2 from the surface. Okay, and the cylinder is having an area of A. Top area is also A, bottom area is also A. Okay, got it. Now what will happen, sir? Forces are going to act here. So horizontally direction, the fluid is acting pressure on this. Very good. Now if you remember, at this point pressure and at this point pressure, same. This point pressure and opposite side pressure, same. The pressure, horizontal direction, pressure are balancing with each other. They are balancing. So there is no force on the horizontal side. So what is the force I am getting? Only on the vertical side. So what will be the pressure force acting here? Sir, rho G H1 A, where rho is the density of the fluid. So what is the pressure force or total force acting on the bottom side? Sir, rho F G H2 A. We all are considering homogeneous fluid. Homogeneous fluid means density constant. Okay. Rho F G H2 A. So in this case now you can tell me F net. Sir, F net is rho F G H2A minus rho F G H1A. So it is total rho F G H2 minus H1 into A. What is H2 minus H1? Sir, height H. So density of fluid G HA. What is H into A? Area into height, cross section area into height, sir. This is volume. So density of height G. This is your volume of solid. Volume of solid. So that's why hence I told you take any shape. Take any shape. Your F net, which is your buoyancy force, is going to be same. Understood? So it does not depend on shape. It only depends on what is your density of the fluid and how much is the volume of the solid. Okay? Pause the video, note it down. Fast. Pause the video, note. So next, write down the theory of this. Okay, buoyancy. Sir, it is whenever a body is completely or partially submerged in the fluid, submerged or immersed, same thing, immersed in a fluid, it's subjected to an upward force, like in the case of our apple, okay, which tends to lift the body up. Sir, why you are writing tends to? We saw it lifted it up. See, I'll give you one more example where it won't lift it up. See, this one is there, right? Correct. Now, what happened? The volume is more, the displaced volume is more. What if I'll keep it like this? What happened? Sir, it sink. It came down. So that means here the buoyancy force was not sufficient enough to overcome the weight of this fluid, weight of the object. Okay, so that's why. But still buoyancy force was working. In the first case you saw it was working. So that's why we use the word tends to. It tends to lift the body up. But if your density of the fluid is not good enough or the volume is not displaced properly, then it will sink only. Okay? Okay, that will come to know subsequent thing. Or buoy it up. So this is also known as buoy. From buoy, it is buoyancy. Buoyancy or buoyancy, however you pronounce. In other words, the tendency of your body immersed in a fluid to be acted upon by a force which act opposite to the gravity force. Gravity always, pulls her downward, but the buoyancy force is upward. Opposite to the force of gravity is known as your what? Buoyancy. Okay? So buoyancy is the tendency. Now buoyant force or upthrust, it's the force which tends to lift the body up under the condition of buoyancy. It acts in opposite to the force of gravity. Because it acts opposite to the force of gravity, that's why if I suppose I will lift something, I lift a book. Okay, let us say I'll lift this book. It's heavy for me. But the same thing if I'll try to sink it down in the water and I'll lift in the water, I'll feel very lighter. So that's why objects feel lighter inside a liquid, because there is a buoyant force which is acting opposite to the force of gravity. So hence we call it a term known as apparent weight. We call it as apparent loss in weight. Okay, we feel like, say there is a well. Okay, you have a bucket of water. Okay, you are trying to pull the bucket of water. The bucket of water, as long as it was inside the water in the well, you feel weightless. As soon as it come up, you have to use more force to lift the bucket up. Understood? So that's why, that means there is an apparent loss of weight of the bucket of water whenever it was inside the liquid, inside the fluid, inside the water. Got my point? That's why, okay, that's why whenever a body is immersed in a fluid, it undergoes an apparent loss of weight. We will study this. What is, how much is apparent loss of weight? We'll study in our next thing. So, understood the concept? Write the theory. Understand the concept? Write the theory. That is how we are going to do it. Okay, so now note it. Okay, so now let us take a container. I have took a container. Okay, in this container I had some liquid. Okay, and in our, what we have done? We have took an apple experiment. Okay, yes or no? If you'll see, there are two marks here, right? This mark is when I take the apple out of this, correct? This is the liquid. When I am keeping the apple inside this, it is occupying some space. That's why the level of water is increasing. So that means the apple is occupying some space. Now what we have done is, we have taken container. Okay, and in this container we had made a hole here. Okay, there is a hole. The hole is in such a way that, and the level of water is such a way that if any small thing I will add into the liquid, the water will start pouring out. Okay, so now here I have placed, okay, now what we have done, we have placed some object here. Okay, let us say the object is having a volume V. The object is having a volume V. So as we have dipped an object here, so the weight will rise, the level of liquid will rise, but there is a hole here. So through this hole, this liquid will start pouring out. Okay, and what I have done, I have smartly I have placed a container here. I have smartly placed a container so that this liquid will deposit in this container. Okay, so this container I took it out. I measured the volume of the liquid. And the volume of the liquid displaced was surprisingly V only. That means how much is the volume of the solid? Same volume of liquid it has displaced. Same volume of liquid it has displaced. This is your Archimedes principle. What Archimedes said? Archimedes was a brilliant Greek mathematician, scientist, physicist, engineer. He invented so many stuff. Okay, let me tell little about your Archimedes. He worked with calculus. Okay, he started sphere, circle, area of a circle and all. That brilliant mathematician, he accurately approximated the value of pi. He worked in pump. Okay, your pulley, lever. That's why it has been told that Archimedes was 1,000 years ahead of his own time. Okay, at what time? These all things he did, and during 287 BC to 212 BC. My God, what a genius guy, isn't it? So that is your Archimedes principle. Whenever a body is partially or fully submerged inside the liquid, the volume of the water or the displaced is nothing but your volume of the solid itself. So we are going to take it little further. Archimedes also gave a mathematical representation. What was our before FB? The force of buoyancy. So the force of buoyancy is the density of fluid multiplied gravity multiplied volume. This is of volume of solid submerged. This is what before we studied. Now from this experiment what we come to know? Sir, the volume submerged is nothing but the volume of liquid displaced, volume of fluid displaced. So from next time onward, now I will write FB, the force of buoyancy is the density of fluid multiplied the volume of the displaced fluid. V, volume of the fluid displaced, multiplied G. So what is Baba? Density into volume. So density into volume is mass multiplied gravity. What is M into G? Sir, this is weight. Weight of what? Weight of the displaced fluid. displaced fluid. So Archimedes told the force of buoyancy is nothing but equal to weight of the volume displaced or weight of the displaced fluid, whose volume is equal to volume of the solid submerged, whose volume is equal to volume of the solid submerged. So the buoyancy force which is acting on a body which is fully or partially submerged in a fluid is equal to nothing but the weight of the liquid displaced, nothing but the weight of the liquid displaced, and the volume of the fluid displaced is nothing but the volume of the solid which is submerged inside the liquid only. So क्या सर immersed, submerged, liquid, displaced, this is your buoyancy. This is your buoyancy. Okay, so you note it down. Then sir, where the force of buoyancy is acting? Where the force of buoyancy is acting? Chalo, we will do that. Already we have also already done. Okay, in our curved surfaces, okay, in the pressure diagram, where the total hydrostatic pressure force is acting. Sir, at the centroid. Similarly, here the force of buoyancy acts at the centroid of the displaced or centroid of the submerged portion, centroid of the submerged portion of the solid. You can take one more example. You take like this, okay? Take a cylinder here. Now only some portion of the solid cylinder is submerged. Only this portion of the cylinder is submerged. If I will take this out and I will make it as a liquid, make it as a volume of liquid, then the centroid of this submerged fluid, this much part, centroid of this is your B, that is your center of buoyancy. Through this your force of buoyancy acts. Okay, the centroid of the volume displaced, the centroid of the volume displaced is your center of buoyancy. Is your center of buoyancy through which your buoyancy force acts. If your fluid is in static equilibrium, if the fluid is in static equilibrium, then the force, the buoyancy and the centroid, is in a common line of action. Are in the common line of action. Why? Because the net force has to be 0. In order to have a net force has to be 0, the net moment also has to be 0. Net moment has to be 0, so they both should act on the same line of action. So the B and J should be at same line of action if your body is in static equilibrium. Okay? Whatever you want to note it down, then you will write the theory of Archimedes principle. Coming to the theory of this, what Archimedes principle say? The buoyant force acting on a body. Buoyant force is where it is acting. See, the fluid, the pressure is acting on the body by the fluid. On the body by the fluid. Okay. Of uniform density, the body is of uniform density, immersed in a fluid, either completely, fully or partially submerged, okay, is equal to weight of the fluid displaced by the body. Because the body now enters some space, okay, it has entered inside the fluid, it occupies some space, so it will displace some amount of fluid. So, displaced by the body, and it acts upward. How the force of buoyancy acts? Acts upward through the centroid of the displaced volume. This we just discussed. Fb is equal to this, which is the weight of the fluid, and weight of the fluid means what? Weight of the fluid displaced by solid part of the body. Okay, solid part of the body. And where it acts? On the center of buoyancy is the point through which the buoyancy force acts. That is, it coincides with the centroid of the volume displaced. Coincides with the centroid of the volume displaced. And suppose you have a completely submerged thing, okay, which is under static equilibrium. Then at this point your G and B coincides. Where G and B coincides, and the buoyancy force acts upward and the weight acts vertically downward. Okay. Why? See, there is an interview question. Why buoyancy comes? Why does buoyancy comes into effect? Because of the varying pressure intensity. Upward we had P1, downward we have P2. Okay, because of this we have hydrostatic force F1 and F2, and the difference of this or the resultant of this force F net is your buoyancy force. So buoyancy comes because of varying pressure intensities. Varying pressure intensities. Come on, pause the video, note it down. Next we are going to study apparent weight. Let's try to understand the concept of apparent weight. AEE, PSUs, apparent weight, numericals are coming. Okay, so try. See this. I have took a weighing balance. Okay, I have took a weighing balance and I am trying to weigh a material. How much kilo it is showing? Sir, it is showing in the dial gauge. It's showing around 5 kg. This is where you are when you are weighing this in air. So when you took the weighing balance in air, it showed how many kilo? 5 kilo. Okay, that is the weight in your air. Weight means you have to multiply acceleration due to gravity. That is your 5 into 10, 50 Newton is your what? Weight in air. Now I have took the weighing balance, okay, along with the weight, and I have kept the weighing balance inside the water tube, inside a tube which has water, okay, and let us say there is an opening here. So as soon as I will keep the weight or the 5 kg inside the water, what will happen? This water will start displacing, yes or no? And here I have collected very cleverly, I have kept a container to measure how much volume of water is displacing. Already we came to know from Archimedes principle that the volume of water displaced is nothing but the volume of the solid immersed only. This Archimedes principle we know. So now this volume is nothing but volume of the liquid, volume of the solid displaced. But here I am seeing a very interesting thing. What is the interesting thing I am able to see? Now the reading in the weighing balance has changed. The reading in the weighing balance has changed. Before in air when I am weighing it, it was showing 5 kilogram. Now when this is inside the water, it is showing me 4 kilogram. It is showing me 4 kilogram. That means I have some loss in weight now. I have some loss in weight. How much is this loss in weight? Sir, this is the weight in air minus your weight in fluid. Correct, na? Yes or no? How much there is a loss in weight? How much you have lost in air, weight in air measured minus the weight in fluid. So how much you have measured in air? 5 into 9.81. 5 into 9. Okay, for simply calculation we are taking 10 minus weight in fluid. How much it is showing? Sir, it is showing 4. So 4 into 10 I will take. So how much I got? I got 10 Newton is the loss in weight. So I am not able to find the 10 Newton. Where did the 10 Newton go? Sir, there is some fluid you have collected here. You measure that. If you measure that, this is nothing but 1 kg. If you put it on a weighing balance, you will get it as 1 kg. 1 kg is how much Newton? So 1 kg into 10 multiply. You got around, you got around 10 Newton. You got around how much? 10 Newton. Isn't it interesting? That means the weight of the liquid displaced, from this problem we know, the weight of the liquid displaced is nothing but the loss in weight. But sir, the weight of the liquid displaced is also your buoyancy force. Exactly, that's the point. The weight of the liquid displaced is also my buoyancy force. So that means this weight, loss in weight is nothing but your upthrust. This is your upthrust or force of buoyancy. Force of buoyancy. That means, okay, note it down first. So isn't it interesting? The loss in weight is nothing but the upthrust or the force of buoyancy itself. So what will be your apparent weight? Sir, apparent weight is going to be your weight in air minus the upthrust. Upthrust is also known as, sir, buoyancy force is also known as buoyancy force. That is your FB. So how much is your apparent weight you found? Sir, buoyancy force is 10 Newton. So this implies your apparent weight equal to 550 Newton minus upthrust is 10 Newton. So you got an apparent weight of how much? 40 Newton. Okay, apparent weight, the calculation. This comes in your exam. Okay. Now please note it down. Okay. So now let us discuss very obvious but fantastic applications of it. Okay. So we knew, sir, FB is equal to your density of fluid multiply G multiply volume that is displaced. Volume displaced. Okay. Okay. Volume displaced by the solid which is submerged inside the fluid. So the buoyancy force is proportional to your fluid density of the fluid. Okay. What if your density of fluid increases? Sir, if density of fluid increases, then my buoyancy force will increase. Buoyancy force will increase. We now know that buoyancy force is acting vertically upward and your gravity is acting vertically downward. Okay? Gravity or your self weight is acting vertically downward. That means if I have to float something, in the liquid, so which has to be more? Sir, that means your FB should be more than the W. If the FB is more than the weight of the fluid, then it will float, because what? Your buoyancy puts it upward Lara. See, like this experiment, apple experiment again. So this, it has some weight, I am keeping it down, but because of the buoyancy force it is coming up. So see what a brilliant this buoyancy thing is. From here we have designed your ship. Okay, ship is also made up of steel only, right? And your tiny pin also made up of steel. If you keep the tiny pin, it sinks. Whether a very big ship, it floats. How it floats? Because the volume displaced by the ship is more. Because the volume displaced by the ship is more, this implies buoyancy force is more. If buoyancy force is more, it floats. But such is not the same case with your tiny steel pin. That's why the steel pin sinks. Very, very good. Now, if your density of fluid is more, buoyancy force is more. That's why in your Dead Sea, which is 24% more denser than your normal sea water, okay, you can float with more of your body above the water. Okay, so now you understood why ship doesn't sink, whereas a small tiny steel pin sinks, and why your Dead Sea literally it is so dense that you float more of your body out of the water, above the water. Okay, so now this density and volume you understood. Okay, very, very good. Now see, think about a submarine. Okay, which is below the liquid. You have a submarine below the liquid. Submarine will be having something known as input and output. Okay, it has to come up. If it has to come up, for moving up, what it needs? Sir, buoyancy force needs less. Buoyancy force needs less means volume displaced should be less. So output it will start taking. Okay. Now, if it has to move down. Okay, means what? It has to move up means force of buoyancy should be more. Means volume should be more. Now it has to move down means force of buoyancy should be less. Anyhow, weight is constant, it cannot change its weight. So force of buoyancy should be less. If force of buoyancy should be less, the volume this should be less. So it will move output. Like it won't take any more water inside. Volume of display should be more, so it will take more and more water inside. That's how a submarine moves up or down in a fluid. Okay, brilliant examples. Okay, your submarines and all. So, but this is obviously, now we are not studying for that. Now we'll go for flotation. Okay, now we'll go to your flotation. Shall I erase? Okay, I am erasing it. So, now, sir, already we have studied if the density is less than density of water. If the density is less than the density of water, a fluid, anything will float, otherwise it will sink. We have studied this, sir. Very, very good. Very, very good. Okay, so we have studied the buoyancy force FB is nothing but equal to weight only. Correct? Huh? We have studied this. That is weight of the fluid. Okay, good. So now let us talk about a case like this. Okay, suppose anything is floating. It is floating. Okay, this body has a average density, rho average body. Okay, it has a height of h. Okay, now this has submerged. This body has submerged h height below, h depth below, and this liquid has a density of fluid. Okay. So, what is the buoyancy force acting here? What is the buoyancy force acting, sir? It is rho fluid multiply G multiply volume of the solid body submerged. Very, very good. Very, very good. We also know that the buoyancy force is equivalent to weight of the liquid displaced. Weight of the liquid displaced, that is mass of the fluid. Okay, multiply G. Multiply G, that is your density of the fluid. Okay, so this implies density of fluid rho F multiply G multiply volume of body submerged is equal to this one, sir, density of fluid multiply. Let's enter into your flotation. Okay, that is your principle of flotation. That flotation, what it is says is the weight of the body floating, the body which is floating is equal to the buoyant force. What is buoyant force? Sir, buoyant force is nothing but the weight of the fluid which is displaced by the body. And the line of action of the weight of the body and the buoyant force acting should be in a same vertical line, so that the moment about any axis is equal to 0. Then only, see, floating, condition of floating is F net 0. What is the condition of floating? Condition of floating is always the net force acting is 0. Net force acting is will be 0 if the horizontal forces, vertical forces in the moment all are in equilibrium. All are net of everything is your 0. Okay, that's why they have to be in the same vertical line. So now let us consider a body. So this is the body. Let us say this is my body, and the density of this is rho body is the density. Okay, rho body is the density. Good. Now this is floating in the liquid. This is floating in the liquid, and the density of the fluid is rho F is the density of the fluid. Okay, and the total height of this body is capital H. Height of this is H. How much it is submerged? Sir, it is submerged through a height of small h. How much it is submerged? Submerged through a height of small h. Okay, and the CG, this is the centroid of the entire body. B is the center of buoyancy. Okay, and you can see the B and G are in the same straight line. Okay, so what does this say, sir? It says the buoyancy force which is acting FB is nothing but equal to the weight of the body itself. It's the weight of the body. So W body. Now what is buoyancy force? Sir, buoyancy force is density of fluid multiply G multiply the volume submerged. MERGD. Okay. This much equal to what? Weight of the body. What is weight of the body? Sir, mass multiply gravity. M into G is the weight of the body. Very, very good. So this implies your density of fluid multiplied gravity multiplied your volume submerged. Okay, volume submerged is equal to this is your density of your body multiply volume of the body. Okay, volume of the body, or I'll write average volume. What I'll write? Next time I'll write what? Average volume. average volume of the body multiplied G. Now G and G cancel. So what you got? Sir, density of fluid multiplied by volume of the submerged portion is nothing but density. Or let us say, sorry, volume of the body. Volume of the body. This one will write average. Average density of the body. Average density of the body multiplied volume of the body. Multiplied your total volume of the body. What volume is this? Total, entire volume, total volume of the body. समझ में आ रहा है? Total, entire volume of the body. What you are trying to find out, sir? I am trying to find out a very fantastic concept. Okay, just I am erasing the second time. Okay, I am trying to find a very fantastic thing. Okay, there go. So this only I am continuing here. This implies the volume of the submerged portion, by volume of the total is nothing but density of the average density of the body divided by density of the fluid. This is a very fantastic equation. This is a very nice equation. Why? Suppose your average density of body is greater than density of fluid, then the volume of fluid submerged portion is more than the volume of total volume. That means what? Entire thing has come. Your what? Total body has now inside the liquid. It has completely sink. That is inside your surface. Okay, I need to erase it, so please note it down. Okay, so we found out the formula. The volume of the submerged portion divided by the total volume of the submerged portion divided by the total volume is nothing but the ratio of the density of average body to the fluid. See, why we are taking average body density? It may not be a uniform. For example, you take a ship. Okay, there are so many stuffs in the ship. Okay, you have air also there. So we take average density instead of direct density. It's not a uniform material. Okay, so for our practical applications we take that. So in such case, let us depict three things. Okay, three things we are going to decide now. Now let us say that average density of the body is greater than the density of the fluid. The average density of the body is greater than the density of fluid. So what happened? Volume submerged should be greater than volume total. Means what? Total body is submerged. Means your body is somewhere here now. It has completely sink. Your body has sink. That is your rho average body is greater than the density of the fluid. So in such case, what happened? This has sink. Now what happens if your average density of body and the density of fluid becomes equal? If it becomes equal, see, it will be floating with this apex upward like this. Like this it will be floating on the top surface. On the top surface of this it will be what? Floating. That is, or we can call it is suspended. We call it is a suspended body. When average density of the body is equal to density of the fluid. Average density of the body is equal to density of the fluid. We call it as like it is suspended. Now what if it is less? What if it is less? If it is less, then it will float. That is the density of body. If the density of average density of the body is less than the density of fluid, then the body will float. Will float. So we have three conditions here. Number one, if a body is immersed in a fluid, it remains at rest at any location in the fluid where its average density is equal to density of the fluid. See, fluid is air also. Fluid means air also. Your hot air balloon or your helium balloon, what they do? Their density is less. So if you open them in the atmosphere, they will be moving upward in the atmosphere until the average density surrounding your balloon is equal to the density of the balloon, matlab density of your helium. That's a helium balloon, isn't it? So as we move up, the density decreases. As we move up, density of the air decreases. There will be a point where the average density of the fluid, that air is a fluid, okay, surrounding the fluid is less. Average density surrounding the fluid is less, means nearly that is equal with the helium. Then at that, up to that point, it will keep on floating. See, this is the same case for your natural convection. Natural convection, what you know, okay, when there is hot summer and all, the density of some portion, the air get heated. When the air is getting warm or heated, its density decreases. Because of that, it becomes lighter. Because of that, it lighter and goes up, okay, through your cold air, it goes up. That's how your natural convection sets up. Natural convection sets up is brilliant. Buoyancy is a brilliant concept. Okay, your hot air balloon also same thing we are doing. You are heating it. By heating, you are reducing the, or you are decreasing the density of the air inside of your hot air balloon. So it moves up until where the density of your outside air and the density of inside air are not becoming equal. Okay, until that it will be moving on. That is your application of this first point. Okay, the second point, it sinks to the bottom when your average density is greater than the density of the fluid, that is submerged, volume submerged becomes more. Next, rise to the surface of the fluid and it floats. It rises to the surface of the fluid and floats when the average density of the body is less than the density of fluid. Same example, your apple wala example. Samajho? That average density is less. That's why even if I am pushing it, average density is less. That's why even if I am applying force and I am pushing it, it comes up. What? Your apple or anything comes up and floats on the surface of the fluid. Okay? The same you can use for your Titanic, that iceberg equation also, iceberg problem. Normally what happens in an iceberg, only this portion is visible, but this portion is totally not visible. How much is this? Nearly 90%. How much is this? Nearly 10%. Why? Your density of ice, how much? Let us say 918 kg per meter cube. Density of your sea water, how much? Nearly 1030 kg per meter cube. So what? Density of ice by density of sea water you do. Normally nearly you will get 10%. So volume submerged. Density of ice water by density of sea water you take. Nearly 90%. So volume submerged is 90%. More volume is submerged. Out of 100% of total volume, 90% of the volume is being submerged. Only 10% of the ice you can see up. Okay, that's what you might have seen. This is success. Okay, this is the hard work you are doing. So always success is only 10% you will find out, but hard work consists of the 90%. Okay. So density of, understood, right? So there are so many things. Sir, if air is surrounded by earth, so air is having some buoyant force on us. Very good question. Very good question. Yes. Air, there is some buoyancy force on us also. There is some buoyancy force on top of us. See, suppose you want to calculate, you can calculate also this buoyancy force. Okay, let me erase this. Okay, so what is the density? What is the buoyancy force by air? Buoyancy force upon air. Sir, this is the rho of air multiplied G by volume of the solid, volume of our human being. We. Let us say my volume is 0.1 meter cube. Let us say my volume is how much? 0.1 meter cube. 1.2 G, let's take 10.1. How much I got? I got 1.2 Newton. So how much buoyancy force is acting on my body? 1.2 Newton. What is my weight? Sir, M into G. Let us say my weight is 80 kg. 80 into 10. So upon 800 Newton, the buoyancy force is 1.2 Newton. So the error is very less. Nearly around 1215 only. Nearly around 0.15, 0.2% you calculate. So that's why we are neglecting, because the buoyancy force is very less. But if you go inside the fluid, the density is 800 times more. That's why the buoyancy force becomes significant. That's why your buoyancy force becomes significant. Are you getting my point? Okay. I think today is too much already we have studied. Okay. You are having any doubts, please write in the comment section. You are most welcome to give constructive suggestions, feedback towards how we are going. Okay, buoyancy is a very important topic. That's why I completed it up to this only. In the next class, we'll be studying about your meta center and stability of floating bodies. Okay, just I have given an introduction to the floating body. And yes, if your body is in floating, okay, when the weight of the body is equal to your buoyancy force, where is the apparent weight? There is no apparent weight. Apparent weight is 0. Okay. So again, if you haven't subscribed to the channel yet, please do subscribe and like, share and comment whatever your doubts are. Thank you. Have a great day ahead.